So thank you for joining us for today's e-showcase, Membrane Aerated Biofilm Reactor, Practice and Innovation, 5 years of full-scale experience at the Yorkville-Bristol Sanitary District. Today's e-showcase is sponsored by Veolia. Today's presenters are Jeff Peeters and Cyrus McMains. Jeff is a professional engineer with specific interests and knowledge in the application of biological remediation techniques, and he's the senior product manager for Veolia Water Technologies and Solutions. Cyrus McMains is the executive director at the Yorkville-Bristol Sanitary District, and he's been operating an MABR system since 2017. And now, I will pass the microphone over to our presenter.
Hi, everyone. Thanks for joining today. So we're going to be sharing, Cyrus and I are sharing with you the topic of membrane aerated biofilm reactor, practice and innovation. I'll be starting with just an overview of MABR technology, and then I'll be passing to Cyrus to share his perspectives as an end user of the technology with 5 years of experience employing it. And then Cyrus will pass to me at the end, and I'm going to share with you a new innovation, a new application of ZeeLung that we call zeeDENSE, which we're also demonstrating at the Yorkville-Bristol Sanitary District. And we'll have 10 minutes at the end for Q&A. So please, as we're going through the presentation today, feel free to add your questions to the Q&A box in the chat, and we will address as many of those as we can through the Q&A at the end of the event. So let's start with an overview of MABR technology. ZeeLung MABR is a next generation biofilm process. The idea is that we use a biomass carrier to support the growth of a biofilm. So we install a media into the activated sludge tank, and we grow a biofilm on that media. So in that respect, the media serves as a support for a biofilm. That allows us to increase the inventory of biomass in our treatment reactors without increasing the mixed liquor concentration. And by having a higher inventory of biomass, that means we have more biomass inventory to do the treatment work. So this concept is not new. This has been employed in the past. What's distinct and unique about MABR is that this carrier material also breathes or transfers oxygen to the biofilm without the use of bubbles. This is a game changer in the principle of how we transfer oxygen into a biological treatment system, and it has important advantages in terms of energy savings, as well as the process opportunities that it unlocks that we'll describe today. The value proposition of MABR is first and foremost process intensification. So what we propose to do is, instead of building new biological tanks, pouring new concrete tanks, adding additional infrastructure to civil infrastructure to a treatment plant to expand capacity or improve nutrient removal, we can add the MABR technology directly into existing tanks to achieve that same goal. And we can achieve up to 50% increase in treatment capacity or improvement in nutrient removal without having to build new infrastructure. So this is the primary benefit of the technology, is to deliver process intensification. Now, as a result of that, it's a more simple solution than a conventional approach because we don't have to build new concrete tanks, and the implementation can happen much more quickly. Typically, we end up operating the system in what we call a hybrid mode of operation, which means that part of the work is done by the MABR biofilm and part of the treatment work is done by the suspended growth process. And that means that we get the benefits of what a attached growth biofilm can do and a suspended growth population can do. And that adds resilience to our overall treatment process. And the cherry on top of all of this is the energy savings. The fact that we're transferring oxygen without the use of bubbles means a step change in oxygen transfer efficiency. And it also opens up opportunities to look at other carbon reduction opportunities like mitigating nitrous oxide emissions. So how does this work? Let's zoom right in and look at the foundation of the product itself. So we start with a reinforcing core. That's the material that you see on the inside, which is like a polyester support, which provides a structural backbone for the product. We then orient a series of polymeric membranes, filaments we call them, around that support. These filaments are about the diameter of your hair, and they're selected, the material is selected for its properties to transfer, to diffuse oxygen. So it doesn't have small pores, it's not transferring bubbles. It's very unique from other types of membranes in the industry. What happens is if we have a concentration gradient of oxygen from the inside to the outside, then molecular O2 will diffuse through the material. And the way we operate this is by sending air, which is at 21% oxygen, down the length of these filaments. We grow a biofilm on the outside of this product, and the biofilm, as it's metabolizing COD or ammonia, is asking for oxygen. It creates an oxygen demand, and that's what drives the concentration, the diffusion of oxygen through the membrane and into the biofilm. So what's unique about the process is twofold. We talked about the bubbleless oxygen transfer delivery, of course, which means high oxygen transfer efficiency. It means we have no alpha factor or fouling associated with other oxygen delivery systems. That also means we have very fine control of oxygen, which opens up really unique process opportunities for the MABR biofilm. And the MABR biofilm itself is what we call a counter-diffusional biofilm. That means from the perspective of the biofilm, the oxygen enters from one side and the pollutants, ammonia and COD, enter from the other side. Because we're delivering oxygen directly to the biofilm via the membrane, there is no oxygen mass limitations, mass transfer limitations. We have very high fluxes of oxygen. It also means that the activity that happens in the biofilm is determined by the kinetics of diffusion. And if you imagine a molecule of ammonia or a molecule of COD, before it can be converted by the bacteria in the biofilm, first it needs to diffuse through the depth of the biofilm. And ammonia is a small molecule, so it has a competitive advantage to reach the oxygen first. So when we sample an MABR biofilm, we find that it's enriched in nitrifiers. And this is foundational to how we apply the technology today, because essentially what we're trying to do is intensify the nitrification and denitrification process in a biological treatment system. So the way we build the product is we start with the filaments, the diameter of your hair. We orient a series of those around what we call a cord that gives us the structural integrity for the product. And we put these cords into a module. That module would be approximately 6 feet tall, and a series of modules into a steel frame we call a cassette. And that cassette becomes the basic building block of the technology. That cassette is supplied with air at a similar pressure that you would supply for a fine bubble aeration system, but a much lower volume. That air runs down the length of all these filaments, oxygenates the biofilm, and we take that exhaust gas that remains at the end, and we can monitor directly in real time how much oxygen has been transferred into the system by using a gas phase oxygen probe. And we also use that residual gas, what we call the exhaust gas, to provide mixing of the cassette to renew substrate at the surface and provide mixing to scour the surface of the biofilm. These cassettes then are installed into the activated sludge tank. So typically this is done in a retrofit, and we would install the cassettes in the anoxic zone so that we can benefit from simultaneous nitrification and denitrification. Nitrification happening in the biofilm, denitrification happening in the outer layers of the biofilm and or the suspended growth anoxic bacteria around the biofilm. And the rest of your activated sludge process remains the same. So it's working in concert with the existing fine bubble aeration system to provide an additional portion of treatment, and solid liquid separation happens via the secondary clarifier. So the way we apply this then is to intensify nitrogen removal. So you can imagine an existing activated sludge system that might have an anoxic zone. We could add ZeeLung cassettes to the anoxic zone to increase capacity. Another approach is taking a plant that removes BOD only today and adding ZeeLung cassettes to augment the aerobic SRT in the biofilm to enable the plant to do nitrification. We've also taken plants that nitrify only and created an anoxic zone to allow the plant to do denitrification, and added ZeeLung cassettes into that anoxic zone to recover the aerobic SRT that was cannibalized to create the anoxic zone. And that can be stretched further by creating an additional volume to allow an anaerobic zone to do biological phosphorus removal. So in all of these scenarios, the function of the MABR is to squeeze the volume that's required to do nitrogen removal which opens up opportunities to do other things with the balance of your treatment assets. So today we have more than 20 plants, full-scale plants of ZeeLung MABR in design, construction, or operation around the world. The one that we're going to focus on today is the first full-scale implementation in North America, the Yorkville-Bristol Sanitary District, which has been in operation for just over 5 years. So I'm going to pass to Cyrus now, and he's going to share some insights and perspectives as an end user of this full-scale facility.
All right, thank you, Jeff. I appreciate that. Hello, everyone. That is not a photo of Yorkville. We'll get to that. First thing, we were formed in 1955. We currently serve a population of about 22,000 people. And if you can see my mouse here, we have about a 34 square mile facility planning area. It's kind of shaped in a north-south ellipse, this whole community. And the beautiful thing here is we have this river bisecting us right in the middle, and our treatment plant is right there. So it helps out. We've got about 15 miles of interceptor, and our treatment facility was first built in 1957. The last major expansion before the MABR system was in 2002, which brought us to single stage nitrification. We have a daily average flow of about 3.5 million gallons of wastewater a day. And then, of course, in 2017, we upgraded our facility to the MABR system for nutrient removal and to increase our BOD capacity in tank. This is an overview, sort of some highlighted areas here. We've got, let's start in the top left here. Our solids digestion is ATAD. That's the autothermophilic aerobic digestion. This is a nice process for us. It helps reduce the overall solids that come out of our facility. In order to have that, we needed some fine screens. We had some coarse screening, some raw sewage pump expansion, but these fine screens down here, they're 1 millimeter by 10 millimeter wedge wire, and that helps out quite a bit with a lot of trash and other things inside of our facility. We added UV disinfection. Of course, we have our secondary clarifiers here and biological nutrient removal reactors. Up here, this white barn, that's kind of our sludge thickening and dewatering. We have gravity belt thickeners and centrifuges. Oh, the one thing to know is we do not have primary treatment. Our fine screens kind of do a good job of that. Here's our little slice of heaven. As you can tell, we've got this little 5-acre peninsula. We've got a creek here on our west property line, the Fox River along the south, and then we do own this property to the west. So it's nice that we're all contained right now, but if we need to expand, or as we need to expand into the future, it becomes very costly to move across that creek. You know, adding additional CapEx for process lines, etc., whether it's intermediate pump stations or relocating the main pump station, etc. Now, why in the world did we go to MABR back in 2017? Well, we had a new phosphorus limit of 1 milligram per liter on a yearly average. I know there's a lot of folks that have more constrained effluent limits than we do. We worked with the community, and we had a watershed work group with our environmental governing body, and we were able to kind of step into it, which seemed appropriate for our area. Now, there's a couple of things here with this plant. We had an increase of population about 20 years ago. We were one of the fastest growing counties in our country. So that meant with newer construction, you've got tighter sewers, you've got low flow fixtures in homes, you have the addition of garbage disposals, and the population increased by 3 times. With that, there's a shift in our influent loading. Originally, we were a little bit more of a rural community and an older community, so we had our hydraulic loading was a little bit higher than our organic loading. And then with these changes, our organic loading started to increase and cause us trouble. So we were running out of organic capacity faster than hydraulic capacity at our facility. And it was largely designed for domestic waste. Well, with the new population, the proximity to Chicago, we're about 30 miles west, has brought some industries into the area. Now, the industries that we have in particular have a very low hydraulic loading to the facility, but they have a high BOD, so a high organic loading. So these are some of the project drivers. Like, I mean, what are we going to do? Here is a picture of what our biological nutrient removal system looked like before the MABR upgrade. Just went in to the first tank, plug flow, aerobic all the way. Now, we wanted to treat biologically for phosphorus, so we had to cannibalize, as Jeff was mentioning, one of our aerobic tanks for anaerobic, so we could get that biological phosphorus removal. In order to help make up some of that lost capacity, the MABR system was installed in that second tank, which is an anoxic tank for us. So the result is essentially an A2O system. So the impact of the upgrade here, we were able to increase our organic treatment capacity in our existing footprint. Now, this is a big deal. My board was very happy to skipping down a little bit to the bottom here. In order for us to go west of that creek and use that property, we were looking at, I think, about 4 times the cost. So spending 25% the cost to get to the place that we needed to go to, I have a very happy board. And the other thing that we had was a very short construction time period to get this thing up and online, which was critical, right? Because you're taking out some of our tanks, which is kind of the heart of the plant. And any upsets or troubles with that or long projects cause trouble. So everybody wins generally when it goes quickly. So that was nice. No major civil works were needed. Now, the biological phosphorus removal system was implemented. This remains an area of opportunity for us. We were able to reduce our phosphorus load substantially, but not quite to the limit that we need to. And that's more of a function of the constraints that we have on site. We do add chemicals for some trimming. So in general, like I mentioned earlier, we had a very happy board. We consider this to be money well spent. Here we go. Another nice photo of our facility. This is what it looks like going in. We just had a crane. You had the tank prepped. You lift up the cassette, drop it in. Here's what it looks like after it's been set. You can see the regular aeration tank here on the left. We kind of cleaned it out a little. We added the support beams across the top. And then as far as the railing goes, you have additional process piping there. You have your air line supply, you have your exhaust line, you have some control wire lines, you have a compressed air line for valve actuation, but not a lot of civil works there. That fits in pretty easily. All right, performance. So the biological phosphorus removal, with some of our chemical trimming over the last 2 years, this is our data on a monthly basis. We were targeting about a 0.5 milligram a liter on our rolling average. You can see we're about 0.44. I think right now we're at 0.55. We kept it a little bit lower just to make sure that we could understand all the adjustments. We've got these levers. How far do we pull the lever? on treating this phosphorus. We wanted to make sure we had some room. You can see the seasonal variation there. So we're feeling a little bit more comfortable with this now, and we're going to start to ratchet that up a little closer to our 1 milligram per liter limit. So with the MABR system, you've got some key performance indicators. There are some performance indicators that we look at. We look at them less frequently today than we did at the beginning when we're trying to learn the system. And one of the things that kind of stands out to us is that once we installed this system here in 2017, the performance has maintained its consistency, right? It keeps on chugging along. So, and this is one of the areas where we will look for step changes in the data to make some adjustments to the system. So the MABR system is fairly minimal maintenance. You know, one of the things that we look for in a treatment plant is something that is highly effective and very low maintenance. One of the ideal pieces of equipment that we have, in my mind, is a clarifier, right? It's just a big tank. It's a pool of water. Water comes in, water goes out, slow spinning drive. You check it once a day with a sludge judge for your blanket, maybe grease it every every month. It's just really low maintenance and it just keeps chugging along. This is similar in the fact that there's really not a lot that we do. We check the KPIs. If there's a change or something, we'll adjust the air supply on our scouring, and then when we're done with that, we'll turn it back to regular. There's really not much else to do. So the MABR cassettes in raw wastewater versus the lab, you know, that's always kind of the big, the big test, right? Can it work? Right? It works in idealized conditions, but when you're the treatment plant, you see everything. At some point in time, you're going to get dumps, you're going to get slugs. And how does it react? Well, uh, about a year after it was installed, we had taken the cassettes out to look at them, and we noticed that they had been really sludged up. The membrane had the biofilm, but the biofilm had grown and grown. The strands were connecting together. It was performing. It was creating this environment for higher life forms, worms, and such to live in. Not ideal. And these cassettes, they have a 10,000 pound limit on them with the support beams and such. So we pulled this thing out. It was about 9,800 pounds, pretty close to the limit. Now, that was due to all this extra sludge. The operating range, and Jeff can, answer this in more detail, but I think it's around 6,000 to 7,000 pounds. So we pulled these things out. We're trying to figure out, what do we have to do? Do we have to scrape these things down, start over? What's going on? And this was a result of some dumping from an industry in town. And so we had taken corrective action since then to help prevent these type of situations from occurring, but it occurs. And Veolia came back, and the MABR folks said, well, you've got the version 1 coarse aerator at the bottom. We've already developed a version 2, and we're installing it on our systems. Let's swap that out, see what happens. They didn't say see what happens. They said they think it's going to work. I said, we'll see what happens. And we put that in. We didn't clean off the membranes. We didn't scrub them down. We didn't take a hose to them. We just put them right back in, all sludged up with their higher life forms, proliferating. And after 4 weeks of this new aerator scour on the bottom, and running a little bit more of an aggressive air scour, we pulled the cassette back out, 6,500 pounds. The thing had sloughed off all that slime, all that extra material, etc. It was amazing. So that's when, you had all of our operators as believers that this system can work and it's not an added pain in their ass. So what we do now with the air scour is anytime we do see a slug come in from an industry or from whoever, or we notice a step change in some of our KPIs, we will operate that air scour a little bit more aggressively for a couple of days, and it cleans things right up. And then we've got our exhaust O2 data. That's kind of what we're looking at for that step change. And we can see there's some variation with the water temperature throughout the calendar year as well. So one of the things that we've also learned here is the system integration is very important. While I said there's not a lot of maintenance to it, it's not like you just drop it in, walk away, right? It has to be designed to work with your environment. So for us up by Chicago, we freeze most of the year. It feels like it right now. So half the year. And just because we've got tubes and pipes and stuff above a mixed liquor tank doesn't mean they're not going to freeze. We actually had a freezing problem in our exhaust air. The high humidity in the exhaust air had frozen, so we had to heat trace some extra lines that we didn't anticipate. Fitting it into your existing SCADA system, having your operators work with familiar control schemes is important. You don't want 6 different control schemes. You want one that they can kind of get in and use. And then the other for us was because we were dropping this into an old aeration tank, we did have some space at the bottom that was void. And we have a concern that sludge is going to settle out at the bottom, heavier particles, or short circuiting. So what we had installed was for our system, we have a jet pump in with a header with jets nozzles along that header, mixes it up. Now we just had the tanks down this last summer, so 8-9 months ago, for some other work we were doing, and we did have some buildup along the bottom, but it wasn't very much, and I think it was proving to us that our mix system was sufficient. So just a couple of things there. So what's next? So for us, we took care of, kind of our organic treatment on our liquid side. Our solids treatment system, that ATAD system is at capacity now. So we do have a major project where we are now moving west of the creek. We've seen continued growth in our community, additional major industries coming into town, residential growth as well at a good clip. And so we are now investing going across the creek there. The next big bottleneck for us, or choke point, is critical path maybe, is the secondary treatment. So when we get that higher flows from I&I, we want to make sure that we can handle that effectively. And our hope is that we can get our existing plant up to a capacity of 6 MGD for our average day, with some minor hydraulic improvements and this solids treatment across the creek. However, we've been working with Veolia here on a way that maybe we can get by without expanding our clarifiers. And I would let Jeff talk about that. It's an exciting thing that we're looking at. We've seen some shifts already. It's a little bit early, but my team is on board with the success that we've had to date. So this is where I will bring my part of the presentation to a close and pass back to Jeff.
Thanks, Cyrus. So we wanted to share with you this next innovation around ZeeLung that we're demonstrating at Cyrus's facility. It's something we call zeeDENSE. And the MABR solution is an effective tool to deliver process intensification. And with this new innovation that we're bringing, we hope to deliver so-called super-intensification. And what we mean by that is that MABR addresses biological bottlenecks. So as Cyrus described for his facility, by adding MABR into his existing tanks, he could increase the treatment capacity of his biological reactors. And the next pinch point he faces is on his secondary clarification. So what we're doing is coupling ZeeLung MABR with INDENSE continuous flow densification, where MABR unlocks the biological capacity and INDENSE unlocks secondary clarification capacity by improving the settling characteristics of the mixed liquor. So showing that same process flow diagram that I did before of the MABR, what we're doing is adding the INDENSE hydrocyclone system to intercept the waste-activated sludge to provide selective wasting of the light solids. So we remove those from the process and returning the heavy solids back into the biological process, which allows us to change the population dynamics of the suspended growth population and improve settling characteristics. And with improved settling characteristics, that allows us to process more flow through existing clarifiers. So this concept of a hydrocyclone for selective wasting is quite simple. We take waste-activated sludge, and before sending that to the solids treatment, we pass it through a hydrocyclone, which imparts gravimetric selection pressure, where we can decouple the hydraulics from the solids, so we can preferentially retain more of the dense population and return those back to the biological process. And we call that the densified activated sludge. Then we take the light stuff, which in fact are the bugs that we don't want in the system, the filaments and so on, and we send those to solids processing. So we're selectively choosing the type of bacteria population that we want in our suspended growth population. Now, this is exciting for a couple of reasons. First, that it now gives us a tool to debottleneck both the biology and the hydraulics. So when a plant has a biological bottleneck, we use MABR to address this. And if there's also a clarification bottleneck, we can add the INDENSE system to decouple to debottleneck the clarification process also. It also gives us another lever in the design of the MABR system. So even in cases where a plant doesn't have a secondary clarification limit, if we can improve the settling characteristics or reduce the SVI more specifically, then that creates an opportunity to operate at higher mixed liquor concentrations. So now we have this lever between shifting the load of treatment that's done in the suspended growth population versus on the MABR, which could perhaps optimize the design of an MABR solution. And the third thing that's the most exciting is looking for the synergies between these two technologies. So it's one thing to apply MABR and continuous flow densification, delivering what they can do independently. It's more exciting to look at the potential benefits of coupling those two technologies. And there are a couple things that show promise here. The first is that they both are work in combination with biological phosphorus removal. I described before that we can use MABR to create space to do biological phosphorus removal, and that's something that was done at the Yorkville plant. INDENSE works best in combination with biological phosphorus removal because the BioP organisms, the PAOs, have good settling characteristics already. So if we start with an initiation for the growth of these dense bacteria through PAOs, and then we retain them in the cyclone, that gives us the best advantage to improve our SVI conditions. There's a hypothesis that the nitrifiers that we're growing on the MABR, if you think about an MABR as a nitrifier farm, it's designed to optimize the growth of nitrifiers, and then we slough them off, and they find their way into the suspended growth biomass and continue to do more work there. Well, there's a hypothesis that those nitrifiers have a higher specific gravity than the general population. And if that's true, there's the chance or the opportunity to retain those sloughed nitrifiers by the hydrocyclone and cycle up the nitrifiers in our biological process to further intensify the nitrogen removal that we can get in existing tanks. So as Cyrus said, we're partnering with the Yorkville-Bristol Sanitary Districts to bolt on a zeeDENSE system at that existing ZeeLung site. The idea here is to see if we can help Cyrus meet his objectives of increasing his secondary clarifier capacity by increasing that by more or less 30%. Also looking at ways we can optimize BioP. Cyrus mentioned that the plant does biological phosphorus removal and trims with chemical. The fact is that the anaerobic zone that exists is a rather short retention time. So anything we can do to optimize the BioP and that constrained retention time could help to offset more of the coagulant costs for phosphorus removal. And also looking for opportunities around OpEx savings, if we can reduce RAS rates, for instance, and save some energy on pumping through the system. So we have commissioned the zeeDENSE system at Yorkville at the end of last year. Implemented in the flow sheet, the only thing that was changed was that we intercepted where the waste activated sludge is taken from the liquid line. And before sending it to thickening, digestion, and dewatering, we first pass it through the zeeDENSE rack. And the zeeDENSE rack then separates the more dense material from the light material. The light material passes through to the solids treatment, and that continues as it was before. And the underflow from the zeeDENSE system returns back to the biological process where we intend to cycle up those more dense bacteria population. And here's an image of what that looks like in practice. So that's in the foreground, you see the anaerobic tank. And then behind that, where I've highlighted the ZeeLung cassettes, this is the anoxic tank with the ZeeLung cassettes installed. And then we have the aerobic tanks thereafter. The zeeDENSE rack has been positioned at the far end above the anaerobic tank to give us good hydraulic conditions to gravity return the underflow back to the biological process. So this has been started up in November. It's a really exciting first implementation of zeeDENSE to show what more can be done with MABR by looking at opportunities to couple it with different technologies. So with that, we're going to open up for some Q&A. While we're doing that, there's some additional resources you can find here. You can welcome to Google ZeeLung, Google zeeDENSE, and you'll find a host of different resources there. Okay, there were some questions, Cyrus, around that story you told about the sludging event. And how is it that we came to realize that there might be a problem? And leading on to that, and maybe this isn't directly related to that event, but in your experience, when you've mentioned before that the one lever you have is if you have this industrial load coming in that you believe might be causing an issue or could cause an issue, and you increase scour, do you see that impacting your final effluent quality? Do you see additional TSS load in your final effluent when you increase the scour to the MABR system, for example?
Right. So one of the things that we looked at was our the oxygen transfer efficiency. You start to see that drop just very slightly. We didn't really think it was a problem when we took out those cassettes. I think we just wanted to look at them, knowing that we had been dumped on by the industry. Because we had seen issues elsewhere in the plant, which is why we knew we were being dumped on. Now, as far as that extra air scour, the MABR system is on the front end of our aeration system. So we don't really notice a higher level of TSS. When we were desludging it just for that 4-week period, we did have higher loadings to our digestion facility. But it wasn't like it all dumped at once.
And on a continuous basis, Cyrus, if we put that event to the side, but in general, how have you seen, for instance, the impact the MABR has had on your settling characteristics or your SVI or your final effluent TSS? Has there been an impact?
Yeah, we haven't really noticed a step change in that when we do that extra air scour. We'll do that air scour. It's just more of a coarse bubble at the bottom, and it just rattles the biofilm a little bit more. I don't think that we could tease out any difference in the mixed liquor loading on the aeration system from when it's on and when it's off. It's not statistically relevant, I guess.
Okay. There's a question here about screening requirements. What's the minimum or what's the required screening for an MABR? You know, at Yorkville, Cyrus has an existing fine screen system that's a wedge wire, I believe, 1 by 10 millimeter. Is that right, Cyrus?
Yeah, that's correct.
And that was pre-existing. That was implemented when the ATAD was added to protect the ATAD. So in general, I can speak to the requirements for MABR. You know, in our experience, if you have a properly designed and operated primary clarifier, that provides sufficient pretreatment for an MABR. If you don't, which is the case of the Yorkville plant, then you would need to add some degree of fine screening to take out the material that could have a negative impact on the MABR cassettes. We were fortunate that the Yorkville plant had existing pretreatment, so there was no upgrade required to the pretreatment at the Yorkville facility. Just another question for you, Cyrus, on operations and maintenance. I mean, when the MABR was added, have you had to add staffing, add resources to the lab to take additional samples required for the MABR? What's your experience been from a resourcing perspective to maintain the equipment?
Yeah, no, that is a concern of ours going into it. We did not add staff for the MABR system. It was an extra blower for us, compressed air system, so air compressor. There are some probes that we added, and so we do calibrate those on a weekly basis. But we are already calibrating our dissolved oxygen probes, our DO probes, on a weekly basis, and so it wasn't really a big adder there as far as extra sampling goes. Maybe an extra hour or two for the week for our lab staff. But yeah, not very big impact at all.
And we've had some questions also on the KPI, so I can provide my input and then you can provide your operation reality, Cyrus. The way we monitor the heartbeat or the pulse of the MABR system is by observing the exhaust gas oxygen concentration. So we send air into the MABR at 21% oxygen. We feed that air at a constant rate. And then we can measure using a exhaust gas O2 sensor, so a gas phase oxygen sensor in real time, how much oxygen remains in the exhaust gas. And that allows us to continuously monitor the oxygen transfer into the process, which is quite cool because it's much more challenging to do that on a fine bubble aeration system. And we find that that exhaust O2 changes depending on the loading conditions to the plant. So if we have a diurnal increase in ammonia concentration, for instance, then there's more demand for oxygen for the nitrifiers, and we see that they consume more oxygen. So we take that exhaust O2 measurement and we convert that using calculations into a specific oxygen transfer rate or an oxygen transfer efficiency. But fundamentally, we use that exhaust O2 data to be the heartbeat and the pulse of how the MABR system is operating. And if we see changes in that over time, that's what we use to inform whether we want to increase the scour for a period of time, for instance, or have a closer look at what might be happening in the system. What's your experience in the field, Cyrus?
Yeah, ours is maybe not quite as technical. We do look at that same exhaust data. So if we see a trend or something starting to shift down, then we will trigger something. But generally, what triggers it for us is we'll get buildup or growth or slime or something on a probe. And we'll notice it when we're calibrating probes. So we expect that our probe data to drifts a little bit. That's why we calibrate every week. So that's not our initial go-to. That's more of a correlation piece when we see any buildup on our equipment in the tank.
Okay, I'm just going to squeeze one more in here and then we're out of time. There's been some great questions, but one is asking about clean in place. And there was another question about, is this like a ZeeWeed membrane for filtration? And I think those two questions are actually related. We're talking about a membrane here, but it's a completely different type of membrane than we're typically used to in our industry. So we're not filtering water. We're not doing solid liquid separation. MABR is a membrane that transfers oxygen to support the growth of a biofilm. And we use it to intensify the biological stage. So because of that, some of the historical things we're familiar with around membranes, like chemical cleaning, don't apply here. We don't chemically clean the membrane because we don't want to destroy the biofilm. So it's a completely different paradigm of how membranes are applied. So I think we'll have to wrap it there. Thanks for your attention today. You're welcome to follow up with myself if you've got any other questions, and I'd be happy to answer those after the webinar. Thanks, Cyrus, for your time. Take care.
Yeah. Thank you. Thanks, everyone.
Great. So I want to take the time to thank Jeff and Cyrus for a great presentation. And another thank you to Veolia for sponsoring today's event. This concludes today's showcase, and we thank you all for attending. The recording will be available at wefbuyersguide.wef.org, and we will send all registrants an email tomorrow with that link. Please visit our event calendar to sign up for future web events, and we hope you have a great day.